over time. And now, in fact, next year maybe I will include some renewables also in this course. The interesting part is whatever may be, even in I rather concentrate mostly on the fossil fuel based systems of waste heat recovery, where any thermal system where some fossil fuel based energy input is there, then obviously subsequent processing may be there. Say in gas turbine, what happening? You want to need extract power from the gas turbine. So what you have to do in the combustion chamber, you have to give some fuel input that will burn, heat will be liberated, and then obviously the hot flue gas will pass to the gas turbine. Then after the power output is obtained from the shaft, then you have got significant amount of heat available at the exhaust of the gas turbine. Now, interestingly, at the exhaust of the gas turbine, and as I've repeatedly mentioned, that any heat doesn't have any significance without its temperature. So, higher the temperature, more useful is the heat, the quantity, whatever it may be. Say you have got some 10 kilojoule of heat at 1000 degrees Celsius, that's a valuable heat. But you have rather 10,000 kilowatt kilojoule of heat at say normal atmospheric temperature, it has got no value, zero value, because unless you have an environment has got a different temperature than that, you cannot at least extract that. You can make in a heat pump system so that that heat can be transferred to a higher temperature, but that heat is not available for any other potential doing work or doing creating energy utilities like refrigeration systems, etc., etc. So any heat available at the normal ambient temperature is of no use, whatever, because the atmosphere itself contains the enormous amount of theoretically infinite amount of heat in the air and water, and in the even in the earth. So any heat specification is according to the temperature of the heat available. And here in this temperature is being critical, the extraction of the heat has also become very critical for energy conservation, because from the viewpoint of the energy conservation, the better the heat utilization through the fuel energy input, more will be the efficiency, and that's the objective of the energy conservation. But the question is, if your system has got certain heat rejected, at what temperature that heat is also important, because that will cause the so-called difficulty of heat utilization. As I told you that if it is at 1000 degrees Celsius, heat utilization is very, I mean, convenient, useful, and it can be done. Existing technology is there. But if it is at, say, ambient temperature today, if I assume it as 35 degrees Celsius, and then your heat available is at 100 degrees Celsius, then obviously there the temperature difference between these two is not that significant. So it's very difficult, not very difficult, but not that convenient as it is possible with 1000 degrees Celsius. So always remember that heat available has its quality determined by the temperature. Now, let me at first define the waste heat as formally as I define it. So waste heat is that heat, you can write it because you can see it from the screen, that is generated in process but dumped to the environment, even though it, sorry, it could, shall, it will not be, it could be, just remove the shall. Okay, I can do it right now, because I otherwise, oh, it could still, that can, then it can happen. So it could still be reused for some useful and economic purpose. So the statement is straightforward. If you use your own language, then the language is such that it is generated in process, but finally dumped to the environment or local atmosphere, though it could be further utilized. Now the question is then how I will determine or rather decide whether some heat will be useful for me or not, because any fossil fuel added system will finally have some rejection. So let's see how does it look like this. So typical process plant flow is something like this. You have certain process plant. It can be a turbine, it can be a boiler, it can be a chemical process plant, it can be a water treatment plant where energy is required. I'm concerned with whether some energy input into required into that process plant in the form of purchased fuel or not. I'm specifically mentioned purchased fuel because that has got the economic significance with respect to energy conservation. Okay, then you have got certain waste fuel that is going out of the process plant, means in the form of incomplete combustion. You know that in IC engine also this happens. Some fuel may not get burned if the proper measures are not taken. Now, actually, I think the design has involved a lot also with the multi-part fuel injection and PFI, etc., where the fuel air mixing is much better, and so the combustion is almost complete. It's not that incomplete combustion happens in modern engines. There may be certain flue gas going out of the system, and oh, don't put it drain water. Let's put it drain liquid. Let me correct it. Otherwise, what or not necessarily it will always be water. Here also I will come later. Oh, I have to put it there. L L I Q U I D. Save slideshow. Current slide. Yeah. So in a general process plant, what will happen that there will be certain purchased fuel input that will make the purpose of the system process plant as the desired output will be obtained from it, and there will be waste fuel from it. That means some fuel will go in the unburned form or unutilized form, and then there will be some liquid come up, not necessarily mandatorily. Say for on gas turbine there is no liquid coming up, maybe smaller amount of liquid coming out due to the in any case if there is any condensations of that flue gas, etc., that's a minor amount. But in many systems, for example, in a heat exchanger, some substantial liquid may come out. So all these options may or may not be there. But this is a general layout of a conceptual process plant where certain gaseous output will be there and simultaneously some drain liquid output may be there. The gaseous output we call it flue gas, and the drain liquid part is basically coming out from the bottom. And then we have got that waste fuel, that means unburned fuel. So if this is the situation, where lies the work potential of extracting the heat? One potential is undoubtedly from the flue gas, because that may have a temperature quite high with respect to the ambient temperature, we can extract the heat. There may be with respect to drain liquid, that means waste liquid, which has got a higher temperature than the local environment, so we can use it also. And there may be the waste fuel that also can be used in some way, because fuel waste means unburned form, means it can be burned to generate more heat. So with this proposition of a typical process plant energy flow, let's see what we can do. So modes of heat recovery. First, if you have the waste fuel, if you want to use it, then the combustion equipment has to be installed there. That means the flue gas, when it is coming out from the system process plant, automatically waste fuel will lie with that, because what is the definition of flue gas? Flue gas is after the entire processing, what gas is coming out and what the fuel was added automatically into the gas. There is no other option, because unless it is a very special system of pure oxygen, etc., etc., the oxygen of the air will be used for the combustion of the fuel. So automatically the waste fuel means that will go in the form of flue gas containing the waste fuel. And then we have so-called flue gas generated. That means subsequent flue gas will generated, means the flue gas input also waste fuel I have shown, but that waste fuel is nothing within the flue gas itself. And then flue gas coming out means what? There will be a temperature increase of the flue gas if you make the combustions of the fuel. Then we have got that heat transfer equipment, means what is the process of this, then exhaust goes out. Then what is the process layout of this particular system is pretty clear: to utilize the waste fuel in the form of waste heat recovery. Because how we find out the waste heat recovery sources? Three. One is waste fuel, another is flue gas, another is the drain liquid. So if it is waste fuel, then initially fuel cannot be extracted from the flue gas. That's not a proposition at all, because that is mixed in the flue gas, means don't try to separate it. It's impossible almost, and useless process. That recovery fuel may not be enough to use for engineering purpose. So burn it. Burn it means temperature of the flue gas will increase, and that will effectively help you for subsequent heat transfer utilization. So then the heated flue gas after the burning of the waste fuel you can use in the heat transfer equipment to going for the exhaust. Now, what is the next? Then I will give a text dictation later on, but just get these figures, then it will be easier for me to discuss. Another option is there are either flue gas or drain liquid. So this drain liquid and flue gas, they are waste heat source if and only if its temperature is higher than the atmospheric temperature. So there is nothing to be burnt in this. I'm assuming that there is almost no waste fuel existing in this flue gas or drain liquid. So then what is your option? You have to go for the, heat exchange process. And then finally the drain liquid will get exhausted and the effective heat will be utilized. Now, if you look into this entire system, there are general process block diagram or process flow diagram is fuel is getting into input into the system. Free waste heat sources may be generated, out of which one may or two may or may not be there. Nothing may or may not be there. But the basic definition of waste heat is two things. One is the fuel, unburned fuel. Another is the heat. And heat means it must be above the environmental temperature or local ambient temperature. It does not mean, say, if a heat is available. This year we have a predicted Indian summer temperature to be very high, and already there is some heat warning. That means maybe it's 45 degrees Celsius somewhere, and if you have 45 degrees Celsius temperature in a country like Iceland, where the current temperature is 0 degrees Celsius, then also still you have some work potential. Means 45-degree doesn't in general mean it has zero potential. It will depend on the local environmental temperature simultaneously. So that is the work potential or exergy, what you call it. So still, on international basis, we have categorized waste heat into three different categories depending on the temperature. Exact value I don't remember, but anyway, I can give the rough value. Then you can just make a check. So, any queries up to this? Then I will give a dictation. Okay, fine. Then just write down a little bit text, because as there is no books, we have to go through this text during exam. Just write down. Uh, in any process plant, in any process plant using fuels, heat generated heat generated through combustion of fuel heat generated through combustion of fuel is supposed to be mostly utilized to its utility to its desired utility form, within bracket, maybe power, comma, heating, refrigeration, etc. Is all these can be utilities. You can use that heat for power. You can heat for rather heating purpose. You can use this for that for cooling also. So, etc. Bracket closed. Most of the heat is converted to its desired utility output. Okay, full stop. However, in any process plant, however, in any process plant, some heat goes out either in the form of unburned fuel or flue gas or drain liquid. Full stop. In fact, unburned fuel, next sentence, in fact, unburned fuel or waste fuel may also remain in the flue gas or in drain liquid. আচ্ছা, এবারে দেখো, ওয়েস্ট ফুয়েল ইন ফ্লু গ্যাস, waste fuel in flue gas may be recovered by burning it in suitable combustion equipment. And subsequently, generated flue gas at a higher temperature may be passed through a heat transfer may be passed through a suitable heat transfer equipment to recover the overall waste heat from the flue gas. Full stop. The next sentence, any waste fuel in the drain liquid may be difficult to utilized may be difficult to utilize as it may demand separation of that fuel it may demand separation of that fuel from the drain liquid. Okay, because you cannot burn it directly. Like in flue gas means there is some oxygen percentage always available, it's in the gaseous form, fuel is already there, but it's not that easy to make that combustion system, because that combustion system is rather much more challenging. Whenever you have this a gas turbine combustor, then enough fuel is there, enough oxygen is there. But in waste fuel burning process, it needs a very specific specialized combustion equipment, because there the fuel amount is very small. Automatically, waste is not that very high concentration, and that flue gas has got the oxygen, and sometimes it may happen that the sufficient oxygen may not be there. So I'm not going into those details. If you want to work in those areas in research or in industry R&D, then you can have some flavor of this, how the waste fuel equipment burning processes actually operate. And this needs a lot of combustion expertise. But the next option, so as you have understood that the waste fuel in the drain liquid is difficult, because in liquid the combustion doesn't happen. So obviously either you have to separate, the separation doesn't make any sense because the amount is so small. Separation from the drain liquid, the fuel is very difficult in most of the cases. So usually we can't do anything with the drain liquid, waste fuel mixed with the drain liquid. But if the waste fuel lies with the flue gas, then obviously we can use it by this two steps. First is the combustion step, second is the heat transfer. And automatically the third step is quite obvious, because in the first step, whatever you have done, the second step, one step will not be there. That means the waste fuel combustion part is not there. But obviously, flue gas or drain liquid, then the both can be utilized. The drain liquid may also have a higher temperature. So just make a sentence for flue gas or drain liquid, for flue gas or drain liquid at a temperature useful to be utilized, at a temperature useful to be utilized, may be used in suitable heat transfer equipment to utilize that waste heat. So we have the story clear what we are going to check in this waste heat recovery process. But now I have mentioned one particular issue repeatedly, that any heat means it is some associated with some temperature. And then temperature means obviously we have certain problem with respect to its utilization if the temperature is not that high. Now, how much high? What is the temperature below which the waste heat may not be that much useful? That also I have given you a hint that it depends on the local ambient temperature. But obviously, the local ambient temperature also goes on varying. So, being in Kolkata during winter, some of the days will have 10 degrees Celsius, and during in summer we may have some 45 degrees Celsius. So, obviously, your system design may not be feasible if you depend on the 45-degree expectation throughout the year. So, most of the time it will remain unutilized. But obviously, if at 45 degree you can use it, maybe in a colder country where the maximum temperature goes below 20 degrees Celsius, there maybe it is useful, but that is a very too small temperature difference to be utilized, because all of you know that the exergy content of a energy depend on the temperature difference between the system temperature and the local ambient temperature. So lesser this difference, lesser will be the work potential. So based on these, go to the next paragraph where I'm giving a thermodynamic input of this waste heat recovery quality parameters and the classification of waste heat. Just write down the value, না value বলবো না, কি বলবো? The waste heat is the quality of waste heat. The quality of waste heat, the quality of waste heat is always decided by its temperature. Higher the difference of temperature between the waste heat and local ambient temperature, between the waste heat and local ambient temperature, higher the difference of temperature between the waste heat and the local ambient temperature, more will be the more will be the utilization potential within bracket, that is exergy, of the waste heat available. Full stop. Generally based on temperature, generally based on temperature, there are three categories of waste heat. There are three categories of waste heat. Within bracket, high temperature, intermediate temperature, and low temperature waste heat. Just let me check whether I can get that temperature value. I have a guess, but I want to give you. It's looking on paper actually. 650 650 medium. Sure. Ah, okay, just write down. Uh, any waste heat available above 650 degrees Celsius, above 650 degrees Celsius may be called high temperature waste heat. Waste heat between 250 and 650 degrees Celsius, waste heat between 250 and 650 degrees Celsius may be called intermediate waste heat or medium waste heat বলে অনেকে intermediate waste heat medium temperature waste heat অথবা intermediate waste heat and any waste heat available below 250 degrees Celsius may be considered as a low temperature waste heat. Acha. So we have defined the temperature, at least what the international community follow. But as you know that the technology, with the technology advances, these definitions also get changed. And currently one of our research interest area is low temperature waste heat recovery. And this where I started teaching this particular course, that time those things were not there at all. Before 23 years, or not that prominent at all. Earlier, what did, I will give the dictation later, but try to understand. Earlier, what was the principle of waste heat recovery is using the waste heat source, you go on generating steam from liquid water. So, what is the problem? If water is the working fluid, which is a very standard working fluid already existing in technology, in power plant, etc., it needs minimum 100 degrees Celsius to boil at atmospheric temperature. That means steam will not be generated. Hot water can be generated. In the district heating system, you can always do that. If it is assured waste heat, you can always have. But the problem is if you want to do something with the steam, which is a more potential thing, because power generation you cannot do with hot water. Power generation you need to generate steam, and that too, not by saturation steam at atmospheric pressure. So it needs at least some superheating, and at least, as you know, that if it expands, then obviously it goes to the two-phase regime. I mean, liquid droplets may start, I mean, so high that the turbine blade erosion will start happening. So what he did actually, what he need actually, we earlier when I started this course, then that time the definition was without 250 degrees, below 250 degrees Celsius, you have very least potential because the water cannot be generated to the steam to sufficient degree of temperature for power generation. In fact, this category was done on the basis of that. But interestingly, this low temperature waste heat, where the terminology still remains below 250, now it has gone up to the level of 70-80 degrees Celsius is useful for power. I will give the text. How do you do? One concept people thought later, and if this is the innovation, why the working fluid has to be water? If we change the working fluid to carbon dioxide, then its boiling temperature is much low. And then if we can make the suitable turbines, etc., in just Rankine cycle, that means the entire thing is just working fluid replaced and suitable devices or components are generated, or rather manufactured. So the carbon dioxide itself will rotate through the entire cycle, and that may be a supercritical carbon Rankine power cycle. Even apart from carbon dioxide, there are many organic fluids which boil at 40 degrees Celsius, organic liquids. So what will happen? If you have a heat source at 80 degrees Celsius, that heat source can be utilized for generating vapor of that organic fluid and then going for the conventional Rankine cycle, just exactly similar to steam cycle. The name is Rankine cycle, but the working fluid is not steam. Then the name came organic Rankine cycle, which is called ORC. So, after this concept has emerged, then the waste heat recovery low temperature definitions has become now a little bit changed. But I still follow the conventional method that below 250, if I mention, that goes to what limit, you don't know. So, obviously, even now 70-80 degrees Celsius temperature utilization papers we have published. And we have a very good utilization potential of these just using these alternative working fluids. তাহলে just write down in the next paragraph. Previously, the waste heat recovery was mostly done by using the working fluid water. By using the working fluid water. As water boils at normal atmospheric pressure, as water boils at normal atmospheric pressure, at only 100 degrees Celsius, any temperature of waste heat below 250 degrees Celsius, below 250 degrees Celsius was of not much use, was of not much use. In fact, next sentence, one of the best example of waste heat recovery at high temperature is the, you have already studied, can you tell me? What is that system called? তোমরা পড়েছো এর আগে? CCGT. Because CCGT is nothing than the waste heat recovery of the gas turbine cycle, তাই না? You can look it as a power cycle, combined power cycle. That's the energy cascading approach. I have looked into that. I have categorized it in that category. But it can be recategorized into a waste heat recovery of the gas cycle to generate the steam power. তাহলে ওখানে 650 এর উপরে টেম্পারেচার আছে বলেই জেনারেট করাও হয়, রাখাও হয়। Keeping that high temperature, you can generate the corresponding steam for the bottoming steam cycle power জন্য। Okay. So one best example of this particular যেটা বলেছিলাম is the CCGT. Okay. Next, right? This is the conventional process what we did earlier. But now I want to mention, because that's why the teaching should be always combined with the research. Unless the current research is known to the teacher, then it will not go to that level. Only the book thing will be there. Just add up, because still I guess very few undergraduate books has those mentioned of those things, but you should be aware of that. Just write down. However, new working fluids, new working fluids with lower boiling point, with lower boiling point other than water are now established as very useful working fluids, very useful working fluids for supply of energy utilities, for supply of energy utilities from the waste heat. If suitable equipment for those, if suitable equipment for those could be made. Okay, because obviously you can understand that this is not that easy. Whenever the properties of water at both steam and liquid form, starting from the water treatment up to the final superheated expansion of the steam in the turbine, everything has been tested, the difficulties over a long period, and technology has been standardized. The standardization of technology did not happen in single day. There were initially blade erosions. The people tried to expand steam up to very low pressure, and they ignored that dryness fraction coming below approximately less than 88%. And in that case, people realized after failure of some of the turbines that you cannot allow the dryness fraction of steam in the expansion process of power output to go below around 90%. So then there was the constant imposed. Like many of these experiences of technologies, new technologies appear only during operation and people go on correcting. That's the engineering always. In problem with these low temperature waste heat recovery, as I'm mentioning, these are not very old technology. These are developed only for last 20 years. Maybe some few papers earlier than that, but only last 20 years the people are trying to develop the different equipment. In fact, we have also given a proposal to Well. If they're interested, we have the theoretical results ready with us with many cycles. If they're interested, they can give their engineering and we can start making at least some of the prototypes to try how this, say, carbon dioxide based cycle or different our property based organic Rankine cycles, what we have published papers, that we can go on trying to make those components. But obviously that risk is, capital risk will be there always. Maybe due to some unknown reasons of chemical corrosions and other things, those things may not last for longer. Thermodynamically these are possible. So developing prototype does not mean it is the end of the system. Before going to commercialization, those have to run at least for several years to find out any difficulties are coming up or not. For example, already I am going through another thesis in IIT Bombay, which is actually in collaboration with an Australian university, Queensland, and there they have used a carbon dioxide based cycle in an energy storage system, and then a phase change energy system, energy storage system. So then the interesting part is the carbon dioxide is now being recommended carbon dioxide cycle even for the nuclear power plant rather than the water. It has certain advantage. But the problem of carbon dioxide cycle is at that very high operating temperature, it has got a very high pressure too. So the components that has to be made to survive at that very high pressure. So obviously the leakage and other things becomes a serious issue in the carbon dioxide because in steam it doesn't go up to that pressure. Steam is basically limited to some. I mean, with the technological experience, we can very easily handle the steam pressure that's operating a steam turbine. But the carbon dioxide cycle has got 220 bar sort of value. So obviously it's a very high pressure and the leakage and other things are there. So technologies means challenges will always be there. But just to add up the last sentence, just put up this area of low temperature waste heat recovery within bracket including geothermal water. You know the geothermal energy is there. I mean it comes in the form of hot water. That's also low temperature. And then tremendous amount of energy can be extracted in some of the countries, not all. Because Finland has got the not Finland, sorry, Iceland has got the highest amount of geothermal energy in their country. You have to have the source. In West Bengal, we have only in Bokreshwar some small geothermal source because geothermal is not always available. Anyway, so just write down. লাস্ট সেন্টেন্সটা কি বললাম বলো তো গুলিয়ে ফেলেছি geothermal energy can be successful with this possible alternative working fluids. Examples of such power cycles may be supercritical CO2 supercritical CO2 cycle within bracket S hyphen CO2 ওটাকে S CO2 বলে supercritical CO2 cycle S hyphen CO2 cycle or organic Rankine cycle ওটাকে ORC বলেই বাজারে চলে organic Rankine cycle within bracket ORC. Next হচ্ছে several innovative power cycles are now reported in research literature and may be a potential user of relatively lower waste heat available. Lower temperature, waste heat available. Relatively lower temperature, waste heat available. That means why I'm giving this sentence is the current definitions of 250 still existing as the low temperature waste heat recovery limit. Now it has gone up to, it was called that below 250. Below 250 there was no nothing mentioned, and that's the safe side. We are safe. Obviously, higher the temperature, easier will be the technology to implement also. Lower the temperature, it is more difficult. That's the thermodynamic principle. All of you know the exergy content decreases, so obviously power extraction may not be that much enough. But with this alternative working fluids, there it's possible and feasible that has been established. Now, what more difficulties will be there during operation is not clear yet because this is an active research area now. But this is undoubtedly a very good research area. In all the advanced countries, they are trying to do that just because of smaller portable systems can be done. And just last sentence I'm giving, combining ejectors, next sentence, combining ejectors, EGECTORS, combining ejectors to these cycles, even refrigeration effect, even refrigeration effect can be created. Acha. I will not go further on this because ejector you don't know, but I guess you know a little bit about if your condenser air extraction process is taught, because there the steam ejection system is used for extraction of the steam by creating extraction of air from the steam by creating a vacuum at the venturi sort of thing. Anyway, so the ejectors one device you can just explore in internet etc. But using ejector we can go for combining that. We can even create a refrigeration effect. That means that will be basically a cogeneration system. Power will be there, refrigeration will be there, because cogeneration not necessarily always has to be heat and power. But though that's most common, people still, industry people still know cogeneration means only heat and power. But co means two, means obviously it can be power and refrigeration. We have at least two, three, four publications on that particular area. That means where we have shown that the refrigeration can be possibly combined with the power using the ejector systems. Okay, well, now ejector হচ্ছে মানে it has got a combinations of nozzle and diffuser with a throat area. So তোমরা তো nozzle expansion সম্ভবত পড়েছো. There you know that it can be depending on the Mach number at the inlet section. It can be the converging diverging nodules can also be created, তাই না? Where you can get the supersonic jet. Okay. এবারে ejector you are putting the same device into a system where the rest part will behave as a diffuser. ম্যাক নাম্বার অ্যাডজাস্ট করে ওর ক্রস সেকশনাল এরিয়া দিয়ে আমি করে দিতে পারি। তাহলে কি হবে, ওখান থেকে যে হাই প্রেশার যে সিস্টেমটা আমি পেয়ে যাবো, হাই প্রেশার ওয়ার্কিং ফ্লুইড হোয়াট এভার আই উইল অ্যাচিভ থ্রু দ্য ইজেক্টর, অটোমেটিক্যালি ইট উইল বি ডান। তার মানে ওর যে টেম্পারেচার যেটা ছিল সেটা কিল্ড হয়ে ওটা প্রেশারে কনভার্টেড হলো। এইবার কিন্তু আমি ওখানে গিয়ে কিন্তু ওই হাই প্রেশার সিস্টেমটা দিয়ে সাবসিকুয়েন্ট পাওয়ার জেনারেশন ইত্যাদিগুলো করে নেবো। এটা হচ্ছে ইজেক্টরের বেসিক প্রিন্সিপল। এবং সেটাকে এক্সপ্যান্ড করিয়ে আই ক্যান ক্রিয়েট দি, মানে থ্রটলিং করে বা এক্সপানশন করিয়ে আই ক্যান ক্রিয়েট দ্য লো টেম্পারেচার এফেক্ট অলসো, যেটাকে রেফ্রিজারেশন করা যায়। পেপারগুলো দেখে বুঝতে পারবে। এটা চট করে বোঝা একটু ডিফিকাল্ট, তোমাকে এই প্রসেসগুলো দেখতে হবে আগে ছবিগুলো। ওকে, ঠিক আছে। এনিথিং কোয়ারিজ আপ টু দিস? নো? ওকে, then come to the different ways of heat recovery techniques. Now I am coming to the actual technology part, which is the purview of the mostly এটা মেকানিক্যাল এবং কেমিক্যাল ইঞ্জিনিয়ারিং এর ডোমেন। এই দুটো এরিয়াই ভালো বোঝে, যে কারণে আমি এটাতে খুব বেশি ওপেন ইলেকট্রিকে পড়াই না। আচ্ছা, এখানে ডিফারেন্ট ওয়েজ অফ হিট রিকভারিতে তাহলে কিন্তু বেসিক্যালি আমি বুঝে গেছি যে দুটো এরিয়া আছে। ওয়ান এরিয়া ইজ বেসিক্যালি আই হ্যাভ টু মেক এ সাকসেসফুল কম্বাসন with low density of waste fuel, and or there will be heat transfer from gas or liquid. Now from your heat transfer তো পড়ানো হয়ে গেছে আগের সেমিস্টারে, পড়ানো হয়ে গেছে। তাহলে heat transfer knowledge, you are all aware that the heat transfer characteristics have some typical features. For example, its heat transfer coefficient depends on between which fluids you are transferring. If it is gas to gas, worst possible, least heat transfer coefficient. Then you can make different enhancement or augmentation technique by adding FEEN and etc., by multipass, all these things you can do. But always gas to gas will have an effective less heat transfer coefficient. Subsequently, Gas to liquid has a little bit improvement, but not gas side will always be poor. That's why the overall heat transfer coefficient will determine on the how much heat transfer coefficient happens on the gas side. But on the liquid side, being little bit more heat transfer, effectively you can get a little bit better heat transfer. Liquid to liquid even improves. Then, if you can go to the two-phase zone, that means one of the fluids or both the fluids are in the phase of changing their phases, then you know that the multi-phase heat transfer process has several, even in some cases, it can be several hundred trends, more than that. That means if you can have a two-phase heat exchange process, always that makes a better heat exchange process. But you may not have the opportunity to get that two-phase directly. But interestingly, I will discuss one device physics only converted into so-called two-phase heat exchange combinations or two-phase heat exchange combinations with enhancement of sub significant enhancement of heat transfer. Let me do one by one. So first option in this heat recovery system is, I'm not going to the combustion part because combustion is much more difficult and without the specialized knowledge, which is not done in undergraduate. In PG, I sometimes taught those things, but here I cannot teach it. Now the question is, gas to gas heat recovery is the one option, because if my waste flue gas is in the gas form, then obviously my recovery gas, which will take heat from that, may be local air or some other it can be carbon dioxide also. So the question is, gas to gas heat exchange means our corresponding equipment will be such that with that poor heat transfer condition, it can accommodate or manage. So what are the possible options? First, I am giving the heat pipe. This is the one of the best possible options where you find out, though the exchange is overall gas to gas, the poorest possible option, how innovatively, interestingly, it has been made converted into combination of two-phase heat exchange process. I'll come then later on. I'm just let me mention one by one, and all these may not be possible to discuss, but at least some discussion can be done. Then after the heat pipe, the second option is the rotating regenerators, or alternately it is called heat wheel. Most probably from heat transfer, you know what is recuperative heat exchange and regenerative heat exchange. Do you remember or recall? Okay. Regenerative means obviously the same heat exchange sections alternately will give the access to the hot fluid and the cold fluid. And during hot fluid passing, it will absorb that particular heat in the matrix, and then in subsequent cycle, the cold fluid will take away that heat. But in recuperative, there is no direct heat exchange, direct contact between these two fluids in any sense. The shell and tube is the example of the recuperative fluid. But the one shell side, there is one fluid, either hot fluid or cold fluid, or in the tube side, there is another fluid. So they get the heat exchange through the, rather, material barrier of the so-called tube walls. Now, third is the run around coil. Just keep the name. If possible, I will discuss a little bit. I don't know whether I will get the time. In gas to gas, the interesting part of run around coil is it's pretty simple. Simply some liquid, specifically water mixed with certain solvents, with increasing its heat capacity. If you can just make a small pump rotating around one heat source and another heat sink, then just simply transfer the heat from the source to the sink. I will show that picture if possible. So run around coil can be another gas to gas heat recovery innovative option. Plate heat exchanger I will not discuss. This is the concept is very simple. Plate heat exchanger means previously we have studied in class. প্লেট হিট এক্সচেঞ্জের ক্লাসে কিছু বলা হয়েছিল না, বলা হয়নি বোধহয়, সম্ভব না, আন্ডার গ্রাজুয়েটে বোধহয় এত সম্ভব নয়, বলা হয়নি তো। তো তোমরা যেটা পড়েছো সেটা হচ্ছে শেল অ্যান্ড টিউব হিট এক্সচেঞ্জেসটাই মোস্টলি পড়েছো, এলএনটিডি মেথড এক্সেট্রা, ইউ হ্যাভ জাস্ট calculated the heat exchange process. But that's the thing we do actually in undergraduate. More than that is not possible. In plate heat exchanger, the concept is very straightforward. Basically, the one of the thermal barrier, that means thermal resistance for heat exchange, is the conduction of that tube's material. So obviously, whatever good conducting material you provide, depending on its thickness, why the thickness is required? Because otherwise the pressure survival is not possible. The outside fluid and the inside fluid pressure will be different. So it must have sufficient strength during heat exchange. So you need the thickness. And thickness as you need, obviously you are increasing your thermal. conductivity resistance. So plate heat exchanger concept is this. No, we have certain processing where the temperature difference and the pressure difference between the two fluids is very small. So to utilize that very small temperature difference, what you have to do, you have to reduce the the resistance of heat flow. For that, if the pressure difference is also low or they are same pressure, both are atmospheric pressure, say, then obviously, if you can make alternative channels separated by very thin, highly conducting material plates, that will not survive if there is a pressure difference because that will simply buckle and break. But if those plates are very thin, but and temperature difference is also not that high, maybe 10 degrees Celsius, but that can be utilized if those alternative channels are separated by very thin conducting plates. Then if you just put the liquids or gases passing through these fluids, automatically you can have certain heat exchange, and that's the plate heat exchanger. In fact, the company Alpha Laval, they are the largest plate heat exchangers manufacturers in the world in Sweden, and I was very lucky to see their best R&D unit in Lund University. It was just beside my place of stay, and that was very interesting to observe how this plate heat exchangers are designed and manufactured. And their manager would come to our lab regularly. That I may not be able to discuss the plate heat exchanger, but I'm trying to giving these flavors to you because how many ways of waste heat recovery is possible, gas to gas, when it is very difficult to extract that particular heat exchange process. But the limitations of plate heat exchanger is that it must operate between very low pressure difference between two heat exchanging fluids. Otherwise, it will not survive. Then convection or tubular recuperator, I am not discuss because you already have been exhaustively exposed to it. So I need not to give any discussion on that because in heat exchanger class, in heat transfer, the heat exchanger is also there. I know in the syllabus and must be it has been discussed. Pebble gas heaters is another very innovative option. You just note down in your all these options, then I will try to pick up some of those as a discussion. All will not be possible to discuss. Pebble gas heaters, there you will find out the interesting part of the pebble gas heaters is it's some sort of regenerative heat exchange process using the solid material in the form of pebbles. Pebbles means you know what is pebble. Marble, গুলির মতো একটা জিনিস আর কি। So using those pebbles, the regenerative heat exchange process can also happen. Rather than the matrix will be that, and that pebble itself moves. Interesting innovation design. I'll show. Pebble gas I will discuss most probably. And then recuperative burner I will not discuss at all because this involves the so-called waste heat recovery from the waste fuel. So these special burners they use it. So out of the seven options I have given, most probably I will discuss three to four maximum. Heat pipe I will surely discuss. Heat wheel maybe I will discuss. Turnaround called small one. The basic concept is not very much required, so I can discuss. And lastly, the pebble gas heaters may be discussed. And plate heat exchangers and the recuperator and recuperative heat burners may not be used. Maybe three or four I will discuss. Then gas to liquid heat recovery. Then you see the situation is changing. There, both side was previously gas to gas. That means gas was the hot fluid, gas was the receiving colder fluid. But in gas to liquid heat recovery, the best possible example is the economizer. You have already studied most probably in power plant. Because any boiler, what does its economizer do? Economizer is the last section of the flue gas going out of the boiler. So there is the basically waste heat if you don't put the economizer. That means that heat will go to the atmosphere. So economizer is a very good example of the so-called waste heat recovery. And there the inside fluid is in most commonly it is water. But economizer can be designed on alternative working fluids also. In our organic Rankine fluid cycles, we use economizer if required, but obviously there the design and engineering is little bit different. Then we have waste heat boiler. This is one possible. This waste heat boiler concept from the name itself is it's a boiler. That means it boils water to steam. But basically it's a heat exchanger because there is no heat addition into it. From some other source, you have some substantial amount of flue gas, then only you can use this waste heat boiler. Generally, these are very common in metallurgical extraction process because in metallurgical extraction process, the Extraction of metal from the ore itself needs significant fuel burning and high temperature operation. So the flue gas going out of the system is having a temperature of more than 1200, 1200 degrees Celsius or 1500 degrees Celsius is pretty common. See how much amount of fuel get wasted, but wasted means unless you don't use it. If you leave it to the atmosphere, unnecessarily all those fuel energy is wasted. So currently, according to BE Bureau of Energy Efficiency, these plants are come under the so-called the chloralkali and other the metal extraction processes come under this particular section of the high potential industries. And in fact, designing wasted boiler based on these is very important. What is the most important challenge in wasted boiler? I will not discuss this in detail in the class because wasted boiler has lots of alternative options and difficulties in engineering. But what I want to mention here, there is one great challenge is whenever you are getting some waste heat from other sources for your boiler or steam generation, then obviously it is as it is, means it will come with a lot of dust and other particles maybe, or maybe some toxic gases are there. So you have to be very cautious of handling those things in your system. Though the heat is available, but heat is not available without any so-called disadvantage or other threats. Always some threats will also be there. That's the engineering life. Then thermal fluid heaters. This I may not be most probably able to discuss. You note it as one of the possible as gas to liquid heater. This is basically different temperature heatings, and in the departmental stores and the shopping mall now these thermal fluid heaters are regularly used as a useful device of waste heat recovery. This is the heating, ventilation, and air conditioning application. In your class, the people are there, they are getting ISHRE award, etc. They might be knowing that in any heating, ventilation, and air conditioning application, there must be different temperature fluids. Say in air conditioning system, to make it oxygen content sufficient, you have to recycle that gas continuously with fresh air. That means you have to fill that confined space because it's a air conditioning is different from refrigeration. Refrigeration there is no such questions. A dead fish or some amount of mutton can be put into oxygen concentration being very low. But a human being cannot be in air conditioned space. Not only the temperature, but also the different air quality is very stringent. You have to have the temperature, you have to have the moisture content, you have to have the proper acceptable oxygen percentage, less or no odor. Air velocity is very important because velocity also have an impact on the comfort of the people. So obviously that based on that, the ASHRAE, American Society of Heating, Refrigeration, Air Conditioning, and ISHRAE, or just a subsequent section of that, in India, they have got their own standard of creating the air conditioning systems. But interestingly, the heating, ventilation, air conditioning come under the same group because whenever there is outside temperature is higher, you need to heat it, and the ventilation process is basically common for both air conditioning and the heating. So obviously using the I mean, the same under the same engineering sections, HVAC is clubbed together under the name of acronym HVAC, heating, ventilation, and air conditioning. In those applications, always there will be certain amount of fluids available which are at different temperatures. Some are at lower temperature, some are at high temperature. So the heat exchange between these two is very much useful for energy conservation. We may not be able to look into that, just giving the hint. Those who are in air conditioning, they can see how this can be made. Then may come the fluidized bed heat exchangers. Fluidization is a different technology. Do you have any idea from power plant what is fluidized bed? No. No or yes? একটু ফ্লুইডাইজ বেড বলার পড়েছো তাই তো? ও তাহলে ব্যাপারটা ফ্লুইডাইজেশনটা জানো, আমি একটু ছোট্ট করে ধরে নেওয়ার চেষ্টা করবো এই ক্লাসে। Okay, so fluidized bed heat exchangers has got very good advantage with respect to the gas to liquid heat exchange process, and how it enhance the heat transfer process. We will check a little bit. Now, the liquid to liquid liquid to liquid heat recovery. That's another possible drain liquid, then working fluid liquid. The first example, shell and tube heat exchangers. Please note these things, options. All options may not be discussed, but you can keep it. And these are not exhaustive also. I'm not claiming these are the all possible, but I'm trying to give them major or most common options, technological options for this waste heat recovery. Shell and tube heat exchangers are obviously you have studied in detail in heat transfer class. This is the most common recuperative heat exchange process. So obviously that can be utilized. Plate heat exchanger again, it can be used for gas to gas, it can be used for liquid to liquid, or it can be used to gas to liquid if there is not much of pressure difference. Generally in gas to gas it's not that effective because temperature difference is also low. So either gas to liquid or liquid to liquid is the best performance of plate heat exchanger. Then waste heat recovery from prime movers. Prime movers, all of you know that it engine concept. So undoubtedly, the first example is the gas turbine, and that's the CCGT comes up. We can put it in either way. Either we can put it as a CCGT as the energy cascading system, or we can put it a waste heat recovery of the gas turbine. Second is currently reciprocating engines. Have a lot of exhaust temperature is much lower than the gas turbine, no doubt about it. But we have also several publications in this area of reciprocating engine waste heat recovery. That means reciprocating engine waste heat finally comes up more than at 250 degrees Celsius. Don't put your hand of the exhaust pipe of an IC engine. That may be very high to burn your skin easily. So, if that can be utilized, in fact, many of the cars have started, especially in cold countries, they have started designing their system so that the waste heat from the car or the final flue gas from the car will be extracted to heat the incoming air. There it is economically feasible. Why? Because the incoming air in a cold country during winter is some sub-zero temperature, maybe minus 20 degrees Celsius. So when your waste heat is going out of the car at the temperature of 200 degrees Celsius, then substantial heat capacity can be included, utilized during the inlet manifold, during the suction of that cold air. But in India, especially in summer, the temperature difference may not be that favorable to make it economically feasible. But we have certain publications with respect to at least one publication has got good citation of in marine. Marine means ship applications. In ship, still the engine is diesel engine. That's considered to be the most suitable because gas turbine may not be that suitable in the steam engine power requirement and the other payload and other issues. So in large ships, large diesel engines are installed for their power purpose, both for power generations. The electricity and other things will be there for lighting, etc., air conditioning, and simultaneously for running the ship. So those reciprocating engines are very large and they have got substantial opportunity to utilize their heat. In fact, one of our publications we have shown that using that organic Rankine cycles and certain water steam generation, that can be a very good combinations of the marine waste heat recovery. And these are the innovative options, and there are we can do it. I may not have much of in the syllabus or question part, but these things, the options you should know if you have the opportunity to do good projects and publications. Then heat recovery from e-incineration plant. This is basically from the name. Previously, what was the concept of incineration? Incineration was mostly used. Incineration means simply burning. So if you want to burn certain waste, because waste consumes space, so what you can do, you can burn it. In earlier was considered to be incineration purpose was only motivated or confined within the removing the waste. But then later on, people with the concept of the energy conservation came up. If I burn, whatever it may be, there may be some heat release, especially if there are some very CV high, little bit more calorific, not high, then it will be fuel, little bit more calorific value waste. Then at least I can have some generate. I have to burn it for environmental purpose, but some heat extract it. And in fact, currently, no incineration is designed only for burning, but used for simultaneously waste heat recovery in that system. But the more challenge, like waste heat boiler, the more challenge for the, this incineration heat recovery is the toxicity management. Means most of the waste after burning creates a lot of chemical toxic substances. So environmental pollution handling of those incineration plant is very much important. Then I will not discuss incineration plant. Heat pump system, I was willing, but I'm not very sure whether I can discuss this heat pump because heat pump, at least I can correlate. During cogeneration, you have seen one scheme where the power generated by the turbine is completely used for the heat pump. That means transfer of heat from low temperature to high temperature. So effectively, there was more utility heat, though the temperature was lower, than the heat input given in the form of fuel. That scheme, I guess that those who are in the present in the class, they can recover, I mean, recall. So the heat pump system can be utilized very usefully of low temperature waste heat pumped to higher temperature and then subsequently utilized in that particular applications. So heat pump purpose will be with some work input depending on good COP, it can increase the temperature of the waste heat so that the category of low temperature waste heat may become high temperature, if not at least intermediate or medium temperature waste heat. That means quality of heat waste heat can be recovered or rather increased by the heat pump system. Unfortunately, heat pump is another big area. I will not discuss much. And last, this is not valid actually current days, though it was when I designed the course that was very important. When the filament bulbs were there the majority of the heat source was going in the form of heat, only smaller amount of light. That means the standard light in a bedroom of a very 10 by 12 feet area. 100 watt was the minimum requirement bulb because 100 watt consumption, 80 watt is going in the form of heat. So it always hot, but only 20% was in the form of light. But this consideration of heat recovery from the lighting system has been completely removed with this generation of LED bulbs. So obviously, this, though I have mentioned it, it has only historical value. Currently, it has got no value in the heat recovery process because lighting systems are so efficient. You cannot have much heat from it to recover. So effectively, designing of that will not be effective unless there is significant quantity. Economically, that may not be justified. So my idea of this, all these presentations were to give you an idea what can be different innovative options of designing the waste heat recovery system. Now I'm coming to the first one, that the device I will discuss. Look into that. This is a heat pipe. Please draw it. If you don't have, if you have any confusion, I can discuss. What is the heat pipe concept is, it's a closed cylinder, completely ended, I mean closed at both sides, of a highly conducting material, mostly copper. It depends on, it can be aluminum also, depending on it at what temperature it operates. So let's start with discussing. It's a copper cylinder sealed at both ends. Then I'll give the text later, try to understand. Then we have certain hot flue gas is passing over this. This is the heat in action. Means as the hot flue gas passes over this, if the inside temperature is lower, what is inside there? Inside, this is basically a wick. The purpose of wick I will discuss later. But inside is filled up with a working fluid that can boil with the heat input to this, from this hot gas available as it will be utilized. So you have to design your heat pump according to the known available hot waste gas, rather waste heat available. So your working fluid also must have to match, and the container material also must have to match, and the wick also have to match with that. That temperature can be for a metallurgical extraction process that can be 1500 degrees Celsius. So then you cannot use copper. You may have to use some other material. And then simultaneously you cannot use that same working fluid and same wick. But it can be operating at the temperature of say 100 degrees Celsius. Then obviously the alternative best possible options may be the copper tubes, and the corresponding working fluid may be some organic fluids. But see the mechanism, I'll give a dictation also. Here the hot gas passes over this. Effectively, if the inside is filled up with a working fluid that can evaporate at a low temperature, then what will happen? Due to this heat addition, it will evaporate. Evaporate means liquid is getting converted from this wick to the vapor form. And as there is enough of vapor, the vapor pressure will build up, and due to the pressure difference, automatically vapor will flow to the other section. And if the vapor flows, here the cold fluid is actually passing over these sides. What will happen to this? Here, as the vapors come here, and the surrounding fluids are comparatively at lower temperature, obviously heat will go out, that means heat out. So what is the steps? First is heat in, second is, the evaporation, third is vapor flow, fourth is condensation. Condensation means if the outside working fluid has got lower temperature, it will condense the vapor that came from this section. So heat is being transferred in this mechanism from this hot source to the low temperature sink or low temperature heat available without any so-called direct contact of these two. Not only that, more important is this, here the heat transfer happened due to evaporation process, two-phase heat exchange, significantly high, and here also another two-phase heat exchange process where condensation happened, just the reverse. Now how the liquid will come back to this, that's the wick does. Once the liquid, it is condensed in the form of liquid droplets. This wicks has got surface tension effect to bring back to this position. So the entire cycle, how it is repeated in a confined conducting material chamber using wicks on the walls, and then a hot and filling up with a suitable working fluid matching with the temperature of evaporation and condensation. Condensation will automatically happen, but evaporation has to be there to match with the boiling temperature. Then obviously, if you pass over one section where this heat will be absorbed by the working fluid, and then the generated vapor will flow through this to the other section, then what will happen? This section is called the evaporator section, and this section is called the condenser section. And the total process is heat in, evaporation, vapor flow, condensation, heat out, and then liquid return back through the wick. And this, in this process of heat pipe, the name is heat pipe, what have we have done? We have converted the gas to gas heat exchange effectively through two TWO2 two-phase heat exchange. That means one is in the form of evaporation, another is in the form of condensation. So the heat pipe has got significant heat transfer enhancement. So heat pipe is very much high value component in engineering applications. So I have to give little bit text, though you have understood from the figure. ফিগারটা যদি পরিষ্কার করে এঁকে নাও তাহলে বুঝতে কোনো অসুবিধা হয় না। হিট পাইপের অঙ্ক করানো যেত, কিন্তু আমি পারবো না, সময় কুলাবে না, এগুলো অনেকগুলো মাল্টি ফিজিক্স ঢোকাতে হয় এগুলোর মধ্যে। এনিওয়ে, জাস্ট আই হ্যাভ টু গিভ দি ব্রিফ ডেসক্রিপশন। এনি কোয়ারিজ? নো? আচ্ছা আচ্ছা, হাইলি করা, তুমি ভুল জানো না, ঠিক জানো। আর এখানেও তো সিস্টেমটা হইতে হবে, ব্যাটারি থার্মাল ম্যানেজমেন্ট সিস্টেমটা তো ওটা লাগবে, ওখানে তো সবকটাই ইউজ হয়, ওখানে ফেস্টেড মেটেরিয়াল ইউজ হয়, হিট পাইপ ইউজ হয়। হিসেবটা খুব সোজা। তোমার তো হিট পাইপ ইজ এ টুল, যেখান থেকে হিট ক্যারি করতে হবে সেখানে বসিয়ে দিলেই হলো, ব্যাটারিতেও করা যেতে পারে, এবং ইট ক্যান বি ইনোভেটিভ অপশনস। ইয়েস, থ্যাংক ইউ। এনি আদার থিংস? নো? তাহলে আমরা লিখে নিই হিট পাইপের ছোট্ট একটা ডেসক্রিপশন ফর দি এক্সাম পারপাস। হিট পাইপ ইজ এ closed cylinder made of a conducting material suitable to the process of heat exchange. And what will be the material? It will be decided on the basis of suitable to the process of heat exchange. Then you write the closed cylinder at both ends. The closed cylinder at both ends is filled with a working fluid, is filled with a working fluid matching with the process of evaporation and condensation process. যদিও এখনো দুটো বলা হয়নি, কিন্তু তোমরা ফিগার থেকে বুঝতে পারছো there is the evaporation and the condensation. আচ্ছা, next write down a wick lining, WICK LINING, a wick lining is provided on the inside wall of the closed container to return the liquid, to return the condensed liquid to the evaporation section, to the evaporator section, to return the condensed liquid to the evaporator section due to capillary action. Full stop. So, the cycle of a heat pipe operation, so the cycle of a heat pipe operation is hit in one দিয়ে লেখো one hit in, you know the meaning now for the picture, then dash two evaporation, three vapor flow dash দিয়ে hyphen দিয়ে or arrow-headed hyphen better to say, যেমন আমরা cycle describe করি, then arrow-headed hyphen condensation, 4, then 5 heat out, 6 liquid return in weak, and make the 6 back to 1. So the cycle is complete. Now, here there is one question, one issue. Uh, Rather than going to the next part, I'm just clarifying that here there are two sections. One is the evaporator, another is the condenser. Now, the interesting part of these two is here the orientation is shown in such a way that evaporation section is at a higher altitude than the condenser section. And so the condensed liquid cannot be transferred due to gravity. But if the condenser section is above evaporator section, that means condensation happens at a higher altitude, then after condensation, what is expected? Through the inside wall of the container, it may percolate. And that percolation, we can make some surface treatment to increase. Engineering material science is very important. And then obviously, no wick will be required because wick will basically cause some problem or other. It helps the heat transfer too in a way, because if the liquids are filled up in that wick, then the heat transfer process makes some sort of matrix provider in the process of heat exchange process. But obviously the liquid layer being on the walls may not be always suitable, but still this is one option. In some applications where the liquid can flow very spontaneously, where the condenser section is above evaporator section, wick may or may not be there. It is still a heat pipe, but in that case, without wick, if it at all operates, I'm telling, don't take that always condenser section being evaporator section, it can be used as a without wick, because wick has got additional effect of the so-called capillary actions, so that the liquid flow become much, assured. Even condenser being above the evaporator, then also you can use the wick for better liquid flow. But in some cases, if the liquid property and the container wall material property can match, then we can remove the wick, and in that case, the flow of liquid will be due to the gravity only. Then the name is little bit different, but that's also a heat pipe. Then you call it thermosiphon, because it's a process of some sort of siphoning of heat in the process. Just একটা paragraph আমরা লিখে নিই। The wick of a heat pipe, the wick of a heat pipe transfers liquid from condenser to the evaporator with the help of capillary action. This enhances the liquid flow. However, if the condenser section is above the evaporator section, the condensed liquid may percolate along the tube walls, along the tube walls or heat pipe walls due to gravity only. However, this flow, this flow, this gravity driven flow, however, this gravity driven flow will depend on many other parameters of the relative properties of the liquid and the container wall. The viscosity, addition effect, এগুলো সব ধরে ব্যাপারটাকে ডিটারমিন করতে হয়। অ্যাডিশন তোমরা জানো ডিফারেন্ট টু ডিফারেন্ট মলিকুলস এর মধ্যে অ্যাট্রাকশনটাকে বলা, কোয়েশন হচ্ছে সেম। কোয়েশনটা ইয়ের ক্ষেত্রে ঘটে, এই আমাদের ক্যাপিলারি অ্যাকশনের ক্ষেত্রে ঘটে, কিন্তু এখানে যখন ওয়ান liquid will flow over the surface of the another metal surface or other conducting material surface, then obviously addition sometimes cause a lot of problem, কোনো ফ্লোই পাওয়া যায় না। সো many characteristics has to be studied to declare, মানে এবার হচ্ছে যে it is at all possible or not that not only depend on the altitude but also on many factors. Just simply add করো, if the wick can be removed in a heat pipe, if the wick can be removed in a heat pipe by arranging the condenser section, by arranging the condenser section above the evaporator section, then it may be called, then maybe not, then it is called, it may become, then it is called a thermosiphon, THERMOSYPHON. You know the siphon process. So that's thermal driven siphon process. Okay, so it's a special case of heat pump. Now, with this input, I'm going to the next part. That means the materials of construction, if you consider the up to a temperature of say 50 degrees Celsius, very low temperature heat exchange process. So freons, all of you are aware, that was previously used as refrigerant material, but currently these are banned actually with respect to the ozone layer depletion process. Those who are in refrigeration process, all of you know. But previously, and currently in heat pump applications, that time I noted in 2020, 2000, now it is 23. Most probably the freon, though I have mentioned is for low temperature, the organic fluids may be used for here. The freon, I may change it in next lecture. I forgot to change it anyway. So freon is now banned with respect to the ozone layer depletion. But you can just look at it as an example. Freon with aluminium up to 50 degrees Celsius can be the combination of materials. Water with copper, 50 to 200 degrees Celsius range. And in fact, in that case, the 50 to 200 doesn't mean that at 50 you can get it. 50 to 200 means the condensation temperature may happen at the 50 degrees Celsius, and 200 degrees Celsius maybe happen at the hot fluid supply side. This is important because being a confined tube, you can make it a vacuum. And if you can make it a vacuum, then obviously your temperature at 50 degrees Celsius, it may be condensed also. So you have to prepare that vacuum according to the required temperature matching of the hot fluid and the cold fluid. Then diphenyl oxide with steel can be another options. These I have taken only from one book. I never worked on the heat pipe. So these are basically to me also the data available. But you can also have a feeling from the internet of whether these have changed significantly currently. Because as I never worked in the heat pipe area, my knowledge is within the classroom teaching only. Then obviously these things are the data I have taken when I prepared this particular slide. Then mercury with stainless steel is also another given at up to 600 degrees Celsius, very high temperature option. There also, and then find out the liquid metal that is also can be used with the so-called refractory tubes, confined tubes, niobium, tantalum, etc. Or ceramic. Ceramic is basically used for insulation, but for very high temperature, 1500 degrees Celsius, these are required for survival or sustaining that very high temperature. Now, the wicks can be woven cloth for low temperature, and this is basically in Bangla যদি বলি অধিকাংশই তোমরা বাংলা বোঝো in kerosene stove. What are those ওই পোলতে যেটাকে বলে those wicks are there. Actually, how the kerosene stove works, there is the cloth driven, this oven cloth driven tube like things that is dipped always in the kerosene, and due to capillary action through that it reaches up to the top, and there actually the firing happens. So firing doesn't go down, but continuously supply of kerosene comes through the capillary action. And noting the kerosene stove burning, you can have a physical feeling of how the heat pipe also operate, because continuously wicks provide that particular liquid supply to the evaporator from the condenser section. Then glass fiber, wire mesh, these are actually used for a little bit higher temperature. So I'm admitting very candidly because I don't work in this area. So these are all collected data for me. I'm not very sure whether these have currently replaced with new material. This is you need not to draw, but I just want to show you that heat pipes are not used as a single entity, which was better for the explaining the physics of that heat pipe heat transfer. But actually, the heat pipes are used always in some cluster, so that you have got enough of hot fluid passing through that with multiple heat pipes, and they are individually just located on a particular frame structure with a splitter plate, and that splitter plate also helps separating the cold fluid and the hot fluid. And splitter plate invariably has to be an insulating material, otherwise the two heat exchange, the temperature difference, there will be a mutual heat exchange process without going through the heat pipes. Okay, this is just a figure to show you, not to, I mean, for your exam purpose, you have to know. And these tubes may be the finned heat pipes, because the finned tubes are always better in heat exchange process, both sides, though I have not shown it. Then areas of applications of heat pipes may be drying, curing, baking. This is for the low temperatures applications. Then brick clean heat recovery means in the brick making process, very high temperature hot flue gas is required. So obviously, after the brick passing over the bricks, then sufficient energy is still available with those bricks. Then that heat recovery can be done in heat pipes. Then there are paper dryers. There are also low temperature applications. Pharmaceuticals, many low temperature heat pipe applications are there, where the heating happens. Generally, the pharmaceuticals heating never go above approximately, I don't know the exact value, not more than 150, even lesser than that, because then the chemicals characteristics will change. So obviously, very low temperature heating process heat pipes are very useful. Textile dryers heat pipes are used. So with this, my idea is to give you the first device which we wanted to discuss with respect to the waste heat recovery. And there, the special feature of this heat pipe is a very active area of whole life research of many people. They are much dedicated to the heat pipe improvement process only. Heat pipe, heat pump, both are very popular research area, both in industry and the academics. And there they go on trying matching with the corresponding heating requirement characteristics, etc., etc. So depending on that, the heat pipe is the first device I have discussed, and there nothing numerical I'm going to discuss in this waste heat recovery processes, because that's very difficult. But one of my students who did his project with me, he was just developing different numerical problems on these topics and trying to solve this. This can be a very good project for undergraduate 1 year project. If somebody is interested, we can always go for that. Anyway, so this is the special feature of the heat pipe is it is converting the gas to gas heat exchange into an equivalent two two-phase heat exchange process. One is the evaporation, another is the condensation. So these combinations of these two two-phase heat exchange is ultimately rendering tremendous amount of good heat exchange from those two gas to gas. Because if you use a recuperative heat exchange, directly one gas passing through the tubes, another passing through the cell side, effectively you don't get any heat exchange. But heat pipe, the corresponding heat exchange is significantly high. আজকে এটা শুরু করব 9:30। 10টা অব্দি তোমরা রাজি আছো? না, রাজি নেই? বেরিয়ে গেছে তাই তো? আমি জানি সেটা বেরিয়ে যাওয়াটাই স্বাভাবিক। এবার কে আর জ্ঞান ট্যান শোনে বেশি? ওরকম একটা ভালো রেজাল্ট নাম্বার পেয়ে গেলেই হয়ে যাবে আর কি। ঠিক আছে, আবার ফেরত আসবে অ্যাটেন্ডেন্স দেওয়ার জন্য। তাহলে একটা কাজ করি, আমরা আজকে এখানে এন্ড করি। এটা একটু সময় লাগতো অবশ্য, 20 মিনিট আছে, তাতে একটু দেরি হয়ে যাবে। রোটেটিং রিজেনারেটর বা হিট হুইল ব্যাপারটাও খুব ইন্টারেস্টিং। এখানে আমরা দেখবো যে এর মধ্যে কনস্ট্যান্ট কি কি আছে। আপ টু হিট পাইপ ইউ ডোন্ট হ্যাভ এনি কোয়ারি, তাই তো? হুম। আমি তো বলছি এটা আমার 2000 সালে যখন আমি বানিয়েছিলাম এই জিনিসগুলো, তারপর আপডেটই করিনি। সেক্ষেত্রে ওটা একটু দেখে নাও, তো সম্ভবত নাও হতে পারে, কিন্তু কোনো এক সময় ছিল। আর এই ডেটাগুলো, এই মেটেরিয়ালের ডেটাগুলো আমার সব নেওয়া হচ্ছে যে বইটা থেকে। সেটা তোমরা একসময় ইউনিভার্সিটিতে একটা কপি ছিল, এখন আর আছে কিনা আমি জানি না, আমাদের ডিপার্টমেন্টাল লাইব্রেরিতে বা সেন্ট্রাল লাইব্রেরিতে ছিল। ডেভিড রি বলে একজন ছিলেন। ডেভিড রি ওয়াজ ইউনিভার্সিটি অফ ম্যারিয়ট, না Marriott what? Canada কিছু নাম, ইউনিভার্সিটিতে ফ্যাকাল্টি ছিলেন। দেন হি স্টার্টেড ওয়ান কোম্পানি অফ হিজ ওন ইন দ্য এরিয়া অফ ওয়েস্ট হিট রিকভারি. So that book was purely on waste heat recovery. So when I making those particular materials and this course material, I took the waste heat recovery from David Rees waste heat recovery book. There, these were there. But I fully agree with you. Most probably, currently, mercury toxicity may not allow it. Because the idea is basically যে কারণে আমাদের এটা টিকলো না, ইভেন্ট সাইকেলটাও টিকলো না। কিন্তু ইভেন্ট সাইকেলে, কম্বাইন্ড সাইকেলে যে পরিমাণ মার্কারি ছিল, একটা ছোট হিট পাইপে মার্কারির পরিমাণ অনেক কম। কিন্তু তা সত্ত্বেও মার্কারিটাকে অ্যাভয়েড করতে পারলেই ভালো। কারণ আমি যখন 2000 সালে এগুলো বানিয়েছি, তখন কিন্তু পিপল ওয়ার নট দ্যাট মাচ কনসার্নড অ্যাবাউট দি এনভায়রনমেন্টাল কম্পোনেন্ট। But currently, the environment has become mostly dominating aspect over all the other economy issues in many applications. ফ্রেয়নগুলো সব বাদ হয়ে গেল। বাদ হয়ে গেল তো ওই জন্যই, এনভায়রনমেন্টের সঙ্গে ওজোন লেয়ারটা যেই ফুটো হয়ে যেতে শুরু করলো, বললো রেফ্রিজারেশন আমাদের কুলিং, আমাদের কমফোর্ট পড়ে, আগে তো বাঁচতে হবে। কারণ আরও কয়েকটা যদি ওজোন লেয়ারের রকম ফুটো তৈরি হয়ে যেত, তাহলে আর আমাদের আল্ট্রাভায়োলেট রে থেকে বাঁচার কোনো উপায় ছিল না। সো I absolutely agree with you. The examples I have given the material, rather I put it to you. You find out the current materials of heat pipes at different range. ইন্টারনেটে এগুলো দিলে সব বেরিয়ে আসে। তুমি আমার জোগাড় করে দিলে, আমি তাহলে নেক্সট লেকচার পাল্টে নেবো। Any other queries? ও দাঁড়াও, তাহলে ওই তোমাদের ক্লাস নোট লেকচারের জন্য না? তোমাদের তো ওগুলো আমি পড়িয়েছি তো তোমাদের, তারপর আবার লেটার দিয়ে কি করবে? ক্লাসে পড়িয়েছি তো ওগুলো সব। টেকনিক্যাল পোর্শনে কোনো অনলাইন ক্লাস হয়েছে নাকি? জেনারেশন তো ইয়েতে কম্বাইন্ড সাইকেল তো পুরোটাই ইয়েতে পড়ালাম বাবা। আহ, না, আমার দিতে কোনো অসুবিধা কিছু নেই। কিন্তু একটাই যেটা সমস্যা হয় যে এইগুলো দিয়ে দিলে অনেক সময় দেখা যায় যে তোমাদের পড়ার জোনটাও কমে যায়। ক্লাস নোটটা কিন্তু দেখতে হবে। মানে শুধু ওই এটা দেখে চলে গেলাম লাস্ট মোমেন্টে, এই স্লাইডগুলো দেখে চলে গেলাম, তাতে কিন্তু মার খেয়ে যাবে। কারণ স্লাইডগুলোর মধ্যে কিন্তু যেভাবে বলা আছে সেটা হচ্ছে তার টিচারের অনেকখানি টেক্সট ম্যাটেরিয়াল আছে। সো কখনোই কিন্তু টেক্সট ম্যাটেরিয়ালগুলো বাদ দিয়ে পরীক্ষার প্রিপারেশনে যেও না, তাহলে বিপদে পড়ে যাবে শুধু স্লাইড দিয়ে। দিয়ে দেবো, কারণ এই তোমাদের জন্যই বানানো। এগুলো এগুলো একসময় আমি এগুলো ইন্ডাস্ট্রিতে প্রচুর লেকচার দিয়েছি এই পিপিটি গুলো দিয়ে। এখন আর ইন্ডাস্ট্রিতে এইগুলো দেই না, কারণ এগুলো আর দিয়ে লাভ নেই, এগুলো লোকে জেনে গেছে। এখন আমি এই লেকচারগুলো আমি পাল্টে নিয়েছি। এখন ধরো ওই এনার্জি কনজারভেশন কম্বাইন্ড উইথ সাস্টেনেবিলিটি, ক্লাইমেট চেঞ্জ, এইগুলোর উপরে ওরা লেকচারে ডাকে। লাস্ট হলদিয়াতে ওদের একটা লোকাল চ্যাপ্টারে বেঙ্গল চেম্বারে যেতেও হয়েছিল। সেখানে ওইটাই টপিকটাই ছিল, এটা যে এনার্জি কনজারভেশন, জেনেসিস, সোর্স অ্যান্ড ইভলিউশন অ্যান্ড রিলেভেন্স উইথ ইন্ডিয়ান ইন্ডাস্ট্রি। এগুলো পাল্টে পাল্টে যায় টপিকগুলো আস্তে আস্তে। আচ্ছা, আজকে তাহলে কে কে আছো এক এক করে আমার একটু বলে যাও দেখি। বিশ্বজ্যোতি নেই তো? নেই। কিংসুক নেই। কিংসুককে দেখছি না আজকে। আচ্ছা, তারপরে হচ্ছে সাহিল সিং নেই।
প্রেজেন্ট স্যার।
সাহিল আছো, সাহিল আছো। আচ্ছা, তারপরে হচ্ছে অমন রাজ মোহতা নেই। তারপরে হচ্ছে শুভদীপ পাল। শুভদীপ জেনারেলি প্রেজেন্ট থাকে, আজকে নেই, আজকে অনেকেই নেই। ঠিক আছে, জগদীশ সাহু নেই। এবার ঋষিকেশ কুমার রাম এটা থাকেই না। আজাহার ইমাম নেই। সাত্বিক মণ্ডল নেই। অয়ন ঘোষ নেই। আয়ুষ কুমার বর্নওয়াল,
Present, sir.
good. You are present in almost all classes. Last class you absent in physical class. Shobik Chaudhary, no. আকাশ গোলদার আছো বোধহয়, দেখলাম তো। আকাশ বাড়ি চলে গেছে, যা দেখ দি। দেখেছিলাম মনে হচ্ছে, খেতে চলে গেছে। কৌস্তুভ ঘোষ, শঙ্কর শুভ্র রায় দেখেছি মনে হচ্ছে। হ্যাঁ, শঙ্কর শুভ্র রায় আছে।
আছি স্যার।
আচ্ছা আচ্ছা, আমান আহমেদ, আমন আহমেদ absent. Then সুমন গুপ্তা মনে হয় দেখেছি।
Yes, sir, present, sir.
You are there, you are there. ঋষভ ধারিওয়াল, না। আচ্ছা, তারপর হচ্ছে সৌগত দাশগুপ্ত, একেও দেখেছি মনে হচ্ছে একবার, না ভুল করেছি তাহলে, দেখিনি। আচ্ছা, স্বাক্ষর বিশ্বাস, ওয়াই দেমান কল্যাণ, নো। অয়ন মাল,
Yes, sir.
অয়ন আছে, অয়নকে দেখা যাচ্ছে। আচ্ছা, তারপর হচ্ছে মোহাম্মদ আসিফ মমিন, মোহাম্মদ আসিফ মমিন নেই। সৌরভ ঘোষাল, তো দেখলাম মনে হলো যে, হ্যাঁ সৌরভ,
Present, sir. Present.
হ্যাঁ, আমি তোমার আইকন দেখেছি, সেটা
Yes,
করছে দেখেছি। ঠিক আছে।
okay.
বিশ্বাস, তারপরে তো রাজু তো আছেই। ঠিক আছে, তাহলে এবার আমাদের নেক্সট বুধবার ক্লাস টেস্ট হচ্ছে। আর তারপরে আমরা বুধবার দিন সন্ধ্যাবেলা একটা ক্লাস আমাকে দিয়ে দাও কষ্ট করে। তাহলে আমরা যেটা করবো তাড়াতাড়ি, হ্যাঁ তাড়াতাড়ি ওয়াইন্ড আপ করে ফেলবো ব্যাপারটাকে। ওয়েস্ট স্ট্রিট রিকভারিতে এরকম 4-5টা আমি তোমাদের বলেই দিচ্ছি সিলেবাস আর কি রয়েছে। ওয়েস্ট স্ট্রিট রিকভারিতে এরকম 4-5টা ইকুইপমেন্ট থাকবে যেগুলোকে একটু হাইলাইট করবো। আমাদের যদি দেখি সময়ের অভাব আছে, কিছু কিছু বাদ দিয়ে দেবো, তবে করলে কিন্তু তোমাদের এগুলো লাভ আছে। ফিজিক্সটা বুঝে গেলে পরে ইন্ডাস্ট্রিতে দেখবে ইন্টারভিউতেও কাজে লাগতে পারে, কারণ এগুলো অনেক সময় এগুলো চলে আসে। কোম্পানিগুলো কে আসে তার উপর ডিপেন্ড করে। যেমন যে নেক্সট দিন যেটা পড়াবো রোটেটিভ রিজেনারেটিভ হুইলস, ওটা কিন্তু পাওয়ার প্ল্যান্টটা তোমাদের জিজ্ঞেস করতেই পারে। পাওয়ার প্ল্যান্টের এয়ার প্রিহিটারটা বেসিক্যালি নাথিং আদার দ্যান রিজেনারেটিভ হুইলস। ওটা ওয়ান অফ দি অ্যাপ্লিকেশনস। একটা তো ওখানে দুরকম জিনিস থাকে, তো ইকোনমাইজার এয়ার প্রিহিটার, দুটোকে একসাথে জেনারেলি করে না। ইকোনমাইজার থাকলে এয়ার প্রিহিটার থাকে না, এয়ার প্রিহিটার থাকলে ডিপেন্ড করে একটা ক্যাপাসিটির উপরে। তাহলে এইগুলো অনুযায়ী কিন্তু এয়ার প্রিহিটারটা যদি ভালো করে জানা থাকে, ওই রিজেনারেটিভ হুইলসটা যদি জানা থাকে, তাহলে কিন্তু অনেক সময় কোনো একটা পাওয়ার প্ল্যান্টের ইন্টারভিউতে কাজে লেগে যেতে পারে। তো এইভাবেই তো শিক্ষাক্ষেত্রে আমরা যাই, সেখানে অঙ্ক করতে ইন্টারভিউতে কেউ বলে না, এই কনসেপচুয়াল পার্টটা নিয়েই ডিসকাশনটা হয়। কারণ কে অঙ্ক করতে দেবে ওখানে, ইন্টারভিউর সময় নেই। আর এছাড়া যে বাকি কম্পোনেন্টগুলো আছে সেইগুলোর মধ্যে আমি দেখবো টাইম অনুযায়ী এগোবো। ফ্লুইডাইজ বেডটা যেহেতু পড়ে এসছে, একটু ধরে নিলে ভালোই হবে। পেবেল বেডটা খুব ইন্টারেস্টিং, যেখানে হচ্ছে সলিড মুভিং রিজেনারেশন প্রসেস দেখানো হবে। আর লাস্টলি এটাতে চলে যাব ওই আরও দুটো একটা কম্পোনেন্ট আমার এখন মনে পড়ছে না কি পড়াবো। আর লাস্টলি চলে যাব হচ্ছে ওয়েস্ট স্ট্রিট রিকভারি ইকোনমিক্স বলি আমরা, যে একটা এক্সিস্টিং সিস্টেমের ওপরে তো ওয়েস্ট স্ট্রিট রিকভারিটা চড়বে। সো whenever you are installing the ওয়েস্ট স্ট্রিট রিকভারি ইকুইপমেন্ট অন an existing system, তখন কিন্তু কস্ট রিকভারিটাকেও ভ্যালিড হতে হবে। অর্থাৎ how much amount of waste heat will be recovered by installing that device, whether that justifies the overall cost of operation and capital cost of the installation of that system. ওটা আসবে লাস্টে, এবং সেখানে ওয়েস্ট স্ট্রিট রিকভারি ইকোনমিক্সটা কিন্তু আমি ডিসকাস করবো। সেখানে মোর ইনভলভ পার্টটা হচ্ছে টাইম ভ্যালু অফ মানি ধরে করা, মানে টাকাটারও আবার ইন্টারেস্ট রেট ইত্যাদি ধরে করা। অত কমপ্লিকেশন আমি যাবো না, সিম্পল দুটো টার্মিনোলজি হয়তো ইউজ করবো, একটা পেব্যাক পিরিয়ড আর একটা হয়তো রিটার্ন অফ ইনভেস্টমেন্ট। পুরো ওয়েস্ট স্ট্রিট রিকভারিটা হয়ে যাবে। তারপর একটু সময় থাকলে আমি এনার্জি স্টোরেজটা একটু ছুঁয়ে দেবো। এনার্জি স্টোরেজ ইজ ভেরি ইম্পর্টেন্ট উইথ রেসপেক্ট টু দ্য রিনিউয়েবল এনার্জি সিস্টেমস, এখন খুব ইম্পর্টেন্ট এরিয়া হিসেবে ইমার্জ করে যাচ্ছে। তাতে ইন্ডিভিজুয়ালগুলোকে ডিসকাস করা সম্ভব হবে না, কিন্তু ওভারঅল বেসিক ফিজিক্সটা, একটা এনার্জি চেইন ফ্লোতে থার্মাল সিস্টেম নিয়েই তো আমরা কনসার্ন। এনার্জি কনজারভেশন পুরোটাই, পুরোটা না ম্যাক্সিমাম, পুরোটা বলবো না। সেখানে একটা ফুয়েল থেকে এনার্জিতে কনভার্টেড হলো হিট, হিট থেকে ওয়ার্ক, ওয়ার্ক থেকে সাবসিকুয়েন্টলি যে ফাইনাল ফর্মে ডেলিভারিটা, এটার মধ্যে বিভিন্ন জায়গায় আমার এনার্জি স্টোরেজের পোটেনশিয়ালটা কোথায় কোথায় আছে, সেটা খুব ইন্টারেস্টিং, এবং সেটাই হয়তো ডিসকাস করে ছেড়ে দেবো। তাহলে তোমাদের সিলেবাস যা আছে, আমার মনে হয় এনার্জি কনজারভেশনের জন্য সাফিসিয়েন্ট একটা ওভারভিউ তোমরা আন্ডার গ্রাজুয়েটের একটা কোর্সে যা পাওয়ার কথা পেয়ে যাবে। আর কিছু নিউমেরিক্যাল প্রবলেমস আমি দেখছি যদি করে রাখতে পারি, সেটা এই কমেন্ট সাইকেল আর কো জেনারেশনের উপরে থাকবে। ওটা করতে হবে, কারণ ওটা থার্মোডাইনামিক্স বেস্ট সাবজেক্ট, অতএব ওখানে কিন্তু নিউমেরিক্যাল প্রবলেমস থাকা উচিত। এইগুলো পারতাম আমি হিট ট্রান্সফারের উপরে কিছু দিতে। দুটো কারণে হয় না, রেডিমেড প্রবলেম থাকে না বলে হয় না, আরেকটা যেটা হয় সাবজেক্টগুলোকে আর একটু ইনডেপথ পড়াতে হবে তাহলে আমাকে, এই প্রত্যেকটা কম্পোনেন্টকে। হিট ট্রান্সফারটা কীভাবে ঘটছে, ওখানে টু ফেজ হিট এক্সচেঞ্জ হলো, তার ওই এন্টায়ার থার্মাল রেজিস্ট্যান্সটা বের করা, এই প্রসেসগুলো পুরোটা করে উঠতে পারি না বলে কোনো বছরই পড়াবো হবে আর পড়াতে পারি না আর কি। এনিওয়ে, গুড নাইট, থ্যাংক ইউ। এই রে, এবার তো কি কোশ্চেন হবে জিজ্ঞেস করবে। কোশ্চেন প্যাটার্ন ওরকম কাছাকাছি বা ওরকমই হবে। আমি বড় ডেরিভেটিভ কোশ্চেন জেনারেলি ক্লাস টেস্টে দিই না। সেখানে যদি উত্তর জানা থাকে টপাটপ হয়ে যাবে, মানে সময় লাগবে না পুরোটা। আর যদি উত্তর জানা না থাকে সেটা ওই
স্যার নিউমেরিক্যাল থাকবে?
নিউমেরিক্যাল তো পড়াইনি তোমাদের, সেজন্য নিউমেরিক্যাল রাখতে পারছি না। তো রাখতে পারলে খুশি হতাম। কিন্তু সেটা তোমাদের সেমিস্টারে কিন্তু নিউমেরিক্যাল থাকবেই। কিন্তু ক্লাস টেস্টে আমি নিউমেরিক্যালটা রাখতে পারলে মন্দ হতো না এবারে। কিন্তু আমি এই ক্লাস টেস্টের আগে তো পড়াতে পারলাম না। আমার নিজেরও কাজের চাপ থাকে, এটা ওটা থাকে। প্রবলেমগুলো দিয়ে দিতে পারলে ১ সপ্তাহ আগে হয়তো আমি এখন এর মধ্যে করিয়েও দিতাম। মানে তোমরা করে আসতে ডিফিকাল্টিস গুলো আমি জাস্ট আনসার করতাম। আমি ধরে, ধরে অঙ্ক কোনোদিন পড়াই না। থিওরি ভালো করে পড়ালে ছাত্রদের নিজেদের অঙ্ক সলভ করতে পারলে তবে লার্নিংটা কমপ্লিট হয়। কিন্তু কোথায় ডিফিকাল্টি হলো আমি হেল্প করে দিই। ওটুকু করে ব্যাপারটাকে হয়ে যেত। কিন্তু সেটা পারলাম না। করতে পারলে ভালোই হতো নিউমেরিক্যাল। কিন্তু নিউমেরিক্যাল ধরে নেওয়া হবে না, ক্লাসে যেহেতু ডিসকাসড হয়নি। আর রাজু, আমাকে তুমি একটু রিমাইন্ডার দিও। আমি যদি ভুলে যাই যে স্যার ক্লাস টেস্টটা M1 বুক করবো। আর ইনফ্যাক্ট তোমরা তোমরা যদি সকালে যাও না, তুমি যদি সকালে গিয়ে পৌঁছো, আমি কালকে ১১টার মধ্যে পৌঁছে যাবো, 10:30টার মধ্যে। আমার ক্লাস আছে ১১টা থেকে, ওয়ার্কশপ কাঠ কাটার ক্লাস। এগুলো তো দিতে হবে, কিছু করার তো নেই। আমার খেয়াল থাকলে আমি হয়তো ওখানেই বুকিংটা করে দেবো। কিন্তু যদি কোনো কারণে বুকিং না পাওয়া যায়, তখন একটু তো প্রবলেম হবেই। কারণ আমি জানি যে মেজরিটি অফ দি স্টুডেন্টকে নিয়ে আমার প্রবলেম হবে না, পাশাপাশি সিটে বসালেও হবে না। কিন্তু একটা দুটো ছেলে এমন অভদ্রের মতো ঘাড় ঘোরাতে থাকবে, আমার মাথা গরম হয়ে যাবে, একটা উত্তেজনার সৃষ্টি হবে। সেজন্য আই ওয়ান্ট অ্যাট লিস্ট M1। দেখি কি করা যায়। একটু কালকে সকাল থেকে তুমিও পৌঁছে যাও একটু। ওই যারা থাকে ওখানে, ওই এরা না, ওই অরূপ টরূপ করে যে ছেলেগুলো থাকে, আমার নাম করে একটু আমাকে ফোন করে নিও। আমি বলে দেবো ওই বুকিংটা অন্তত মেরে দিতে কালকে, যাতে আর কেউ না পায়। হুম? সেক্ষেত্রে তুমি বাধ্য হই আমি এমন ক্লাস টেস্ট যদি দেখি ১১টা থেকে কারোর পড়ে গেছে, আমি তো ১০টা থেকে ১০:৪৫ অব্দি আমার ক্লাস টেস্ট নিতে বাধ্য হবো। কি করবো, নিতে হবে আমাকে, তো ছেড়ে দেওয়া যাবে না আমাকে। আমি তোমাদের ১২টা অব্দি যেহেতু টাইম আছে, আশা করি তার মধ্যে হয়ে যাওয়া উচিত আর কি। একটা স্লট আমরা পেয়ে যাবো কালকে। একটু দেখো, ওই রুম বুকিংটা খুব জরুরি, আমি ভুলে গেছি। গুড নাইট, বাই।